Am I visible and audible to everyone? Yes. So today, guys, welcome to all this JEE Byte session, and today we are going to discuss about the oscillations. Okay, and this appears to be very difficult as well as a very important topic as far as the JEE exam is concerned. Okay, because in this, lot of topics are involved, basically the mechanics part. So today we are going to discuss, and we are going to take a few questions on this. Okay, so let's just start off this one. Okay, so I'm going to start with the basic terms here. So, guys, here the main important part is the SHM, the simple harmonic motion. Okay, so let's just take an example of a pendulum, or you can take an example of spring mass system as well. So, sorry, guys, just forgot to say hi to everybody. Hello, Gurfan. Hello, Hari, Meghna, all of you. Great welcome, guys. So yes, I do have a pendulum here. Okay, so this one is the mean position. Okay, this one is the mean position, and it just oscillates, or it is just doing the to and fro motion about its mean position. These are the one which are the extreme positions. Okay, so how can we write the equation here about the oscillation? That would be x is equals to a sine omega t, where a is the amplitude. This one I'm going to represent as A, because A is the amplitude and it is being oscillated like in this way. So how would you calculate the velocity from here? You just need to differentiate it. How would you do that? Dx upon dt is nothing, just the V. So that is coming out to be A omega cos omega t, isn't it? Right? So if you are doing it double derivative, if you are doing differentiation again, so you will be getting the acceleration is nothing but dv upon dt. So you are doing the differentiation of this particular term. So this is a omega cos omega t, right? So now you can see here I'll be getting minus a omega square sine omega t, or basically I can write here as a is equals to minus, this is what, a sine omega t is what, this is nothing but the x. I'm going to write it here, this entire portion, right, is nothing but x, right? So I can put it here as omega square x, right? This is the acceleration in SHM. Okay, so yes, so you just need to see the acceleration here. Let me just put it in the words here, just a moment. So if I'm going to build up a graph here, so what you can see here, that I have, this is my acceleration and the displacement axis. Here x is the displacement, guys, remember this is the displacement. Okay, so what is happening here, you can see that I just need to extend this axis. Yeah, if you're just building a graph between acceleration and the displacement, you can see here that the acceleration is directly proportional to the mean distance, to the displacement here. Okay, so here, and you can see the negative sign means it is always towards the mean position. It is always towards the mean position. If I'm going to draw the graph here, that would be a linear line, and that too with a negative slope. That is what we are going to see here. See, this is how it is being represented. Okay, so this is nothing but the graph between the acceleration and x, means the displacement and the acceleration as far as the SHM is concerned. This is nothing but the omega square x, right? So this is the graph, this is the variation of the acceleration with the displacement. So guys, one more important thing in this is, like, they will give you some system, some random system, and they will ask you about the frequency. or they may ask you about the time period. So we can just take a basic fundamental system here, that I'm going to take it, just a moment guys. I'm going to take it up here. Like if I take it this one, the spring mass system here, suppose I have a spring. Okay, it has a spring constant k and its mass is m, and it is being oscillated about this mean position, like to and fro, right? So what I'm going to do here is, you just need to write the energy equation. This is one of the beautiful method in the oscillation part, where you just write the equation of the energy, you just differentiate it, because thing is, the energy, the total energy of the system has to be constant. Okay, so we can just write the equation of the energy here and derive whatever we wanted here. Like they may ask you about the frequency, they may ask you about the time period. So this is one of the beautiful method. I'll tell you how it is. Suppose it is being stretched by a small position, like you can say it is being just stretched by a small distance like x. So this particular mass will be having both the velocity as well as it has been stretched by a small amount x. So the entire system may have potential as well as the kinetic energy, isn't it? So the total energy, I'm going to write it as potential energy plus kinetic energy, right? So here, what would be the potential energy as it is being stretched by by x amount, so half kx square, right? And kinetic energy is nothing but half mv square. This is the amount of total energy, and it has to be constant, because energy is, you know, that conservation of energy, neither created nor destroyed, right? So it has to be transformed from one form to another. Like here, the potential is being converted into kinetic, and kinetic is being converted into potential. This is how the system is working. Okay, so what I'm going to do is, I'm going to differentiate, right? As you know that this is a constant, so differentiation of this particular energy has to be 0, and that is equals to d upon dt of half kx square plus d upon dt of half mv square, means the differentiation of the potential as well as the kinetic energy, right? So what would we get here? That would be a half 2kx dx upon dt, and here half 2mv, right, dv upon dt. So you know that here we can just, you know, cancel these terms here. So if you do all the mathematics here, so you are getting kxv, because dx upon dt is nothing but v, plus mv. What is that? dv upon dt is nothing but a. So if you're calculating the acceleration from it, what would you get? You will be getting minus kx v upon mv, or basically you're getting minus kx upon m. So guys, I just told you what is the acceleration depends on which factors in the SHM. So that is nothing but a is coming out to be minus omega square x. This is the general equation, right? And here it is minus kx upon m. So if I ask you what would be the value of omega here, so you can easily calculate under root k by m, right? Right, guys? So here I'm going to write it again, that is minus omega square x is minus kx upon m. It shows that this motion, this spring mass system motion, is a SHM, right? So here I can calculate that this is under root k by m. Or basically, you know that this is 2 pi upon t. If somebody asks you what is the time period of this spring mass system, you can easily tell that the time period has to be just a moment, time period has to be 2 pi under root m by k. This is what you study, right? Any problem in understanding this one, guys? And any system, if they give you any system, what you can do is you just need to write a energy equation, you just need to differentiate it, and you can just figure out the the value of frequency or the time period. If somebody asks you the frequency here, again it would be nothing but this one, because nu is what, 1 upon t, right? So now guys, I can we can just take a few questions on this. Okay, the last year questions that was asked in IIT JEE. Okay, so I have I have a few questions with me. So this question I have here: for a simple pendulum, a graph is plotted between the kinetic energy, the graph is plotted between its kinetic energy and the potential energy against the displacement. Which one of the following represent correctly? Means, which of the following variation is the correct representation of the kinetic as well as the potential energy? So how would you do that? By looking the graph, you can see you can see that most of the graphs are nothing but the parabolic, right? Most of the graphs are nothing but the parabolic, and it should be actually, because half kx square, it has a variation x square with the potential energy, that is nothing but a parabolic, right? So what we can see here, or what should be your observation here is, guys, you can see here. Okay, let me just draw an illustration for all of you. You can take a pendulum here, because they have just given a pendulum example, right? So you can see here, see, or you can see here, see, potential energy, guys, just a moment. Potential energy is nothing we can represent as half kx square, if you're just considering about the spring mass system as well. So more the distance, or you can say more the displacement from the mean position, more will be the potential energy. You can see here the variation for the first graph. For the first graph, you can see here the potential energy, more the distance, this one, the potential energy is getting zero. So this cannot be, right? For this one, see guys, one more thing I just need to tell you, the total energy has to be constant, right? Total energy has to be constant. So that is a sum of nothing but the potential as well as the kinetic, right? So the if you are going to consider this C part, so what you are going to do, you will be getting zero all the time. That is not valid at all. So we need to just neglect this one as well. We need to discard this option as well, right? C option cannot be true, A option cannot be true, right? And I just told you they are varying with the parabolic as well. So we are just looking to the B option here. You can see the potential energy is zero at the mean position. You can see here, if you are putting x equals to 0, so they will it will give you nothing but the potential energy would be 0, isn't it? Potential energy at x equals to 0 is nothing but the 0. So this graph, the potential energy graph, has to start from the 0, isn't it? Right? So this one is getting started from 0, right? And you can see one more thing, that half mv square is nothing but kinetic energy, right? And guys, if you remember, I just told you excuse me, I just told you that x is equals to a sine omega t, right? And v, how can you calculate? That is differentiation of this one, though this is a omega cos omega t. So guys, you can see here at t equals to 0, the v has to be maximum, isn't it? And that is equals to a omega. So at time equals to 0, the velocity will be maximum. So kinetic energy maximum at the mean position. Okay? And potential energy is maximum at extreme position. Okay? So by looking these graphs here, what can you predict from here? You can see here the kinetic energy is maximum at the mean position and potential energy is minimum at here. And all you can see is these two graphs are varying with the parabolic nature. So that's why this graph is pretty good. We are neglecting this graph. You can see why, because here the variation the variation of the kinetic energy and the potential energy is not parabolic at all. Okay, so B would be the right one. Okay, so let's just move on. Another question, guys. Here, the xt graph means the displacement and the time graph of a particle undergoing simple harmonic motion is shown below. The acceleration of the particle at t equals to 4 by 3 seconds. So we just need to figure it out. The particle acceleration is given as t equals to 4 seconds. Okay, so now I'm going to take up this question here. Okay, so guys, you can see here what would be the time period. It is coming out to be 8, right? So if it is coming out to be 8, so t is given as 8, right, seconds. So what would be the frequency? Or you can say what would be the omega, that is 2 pi upon t. That is coming out to be 2 pi upon 8, coming out to be pi by 4 seconds, isn't it? Right? It is coming out to be pi by 4 second omega. And if I ask you what is the acceleration term, I just told you acceleration is nothing but minus omega square x, isn't it? In the case of the SHM, the acceleration is coming out to be minus omega square x, right? So here, the minus omega square, how would you put this one? This one as pi square upon 16, right? And x, I'm leaving it as it is. So I just need to put the value of x at t equals to 4 by 3 seconds. That's what we need to calculate, right? So this is 4 upon 3 seconds. So it is coming out to be, what is x? You can represent as x is a sine omega t, right? That is, what is a? That is 1, right? So 1 into sine. What is omega? That is pi by 4. And what is the time period? This is given as, what is the time here? 4 by 3. So 4 upon 3. So this is coming out to be sine pi by 3. What is sine pi by 3? That is nothing but under root 3 upon 2. So x is coming out to be under root 3 upon 2, right? So here you can see this is coming out to be under root 3 upon 2. So now you can see here that x at t equals to 4 by 3 is nothing but under root 3 by 2. So what would be the acceleration at t equals to 4 by 3? That is nothing but minus omega square x. We know both the things at t equals to 4 by 3. This is minus pi square upon 16. This is under root 3 upon 2. It's coming out to be under root 3 pi square upon 32. So this is the acceleration at t equals to 4 by 3. Okay, so this one, guys, is that clear with everybody? Right? Okay, fine. So I'm going to take up a last question here. See, I have a wooden block performs SHM on a frictionless surface with a frequency nu naught. The block carries a charge of Q on its surface. If now a uniform electric field is switched on, the SHM of the block will be same frequency with the shifted mean position, same frequency with the same mean position, change frequency with the shifted mean position, or change frequency with the same mean position. I just told you guys what is the formula for frequency, or you can say the time period here. The time period here is 2 pi under root m upon k, or you can see that the frequency is 1 upon 2 pi under root k by m, right? If you're changing the external, you are just providing an external force that is nothing but the QE, right? So there is no effect on all these terms here. There is no effect on all these terms here, okay? That's why the frequency has to remain constant. Okay, but guys, when we provide a constant force, The thing is, the variable force creates some problem in the frequency, but whenever we providing the constant force, the mean position getting changed. So according to all these factors, we are going to choose up an option that is nothing but the A, of the same frequency but with a shifted mean position. That has to be correct. Okay, so guys, these are the questions that we have taken today. Okay, and this is like one of the important topics, guys, so please do as many as questions you guys can. And guys, that's all from my side. Thank you so much, and next time we'll be coming up with a new topic. Okay, or probably with the oscillations part 2 actually. Okay, so thank you so much, guys, and you can just check out these links. Thank you so much for attending the session. Thank you. Bye bye, take care.